Today, we'll be exploring how the physical properties of cornstarch-based bioplastics change when mixed with different additives, such as glycerol, sugar, and glue. Specifically, their flexibility and tensile strength will be measured, since they are the most useful properties in industry applications such as packaging, medicine, and agriculture. Bioplastics are a sustainable alternative to traditional petrochemical plastics, but although bioplastics are made from organic polymers, the additives required to make them functional often aren't biodegradable, meaning that not all bioplastics break down naturally. As a result, scientists face the challenge of balancing environmental sustainability with material durability when it comes to bioplastics. I measured the synthesized bioplastics flexibility and tensile strength in this study on a qualitative observed scale of 1 to 5 for each. So, what really is a polymer? It's a big, chain-line molecule made from lots of the same repeating little molecule called a monomer. Bioplastics, which is what we're investigating today, fall under this. There are normally two types of these polymers, addition and condensation. Addition polymers, such as PVC, Teflon, also known as PTFE, and polyethylene, form when monomers with double bonds, such as ethylene, open up these double bonds and join together without releasing byproducts. Condensation polymers, on the other hand, form when functional groups, such as carboxylic acid or hydroxyl groups, react with each other, forming small molecules like water. For example, polyester forms by esterification of a diol's hydroxyl group and a dicarboxylic acid's carboxylic acid group. It's also important to know the molecular properties of our additives, since they're what we're investigating. Glycerol softens bioplastics by spacing out the polymer chains. PVA glue increases strength through its hydrogen bonding, and sugar increases brittleness by promoting crystallinity, despite forming some hydrogen bonds. For the method, each bioplastic sample was made by heating a mixture of cornstarch, water, vinegar, and a set combination of additive. One is glycerol only, half glycerol and sugar, and then half glycerol and PVA glue, on a hot plate for 10 minutes. Once the mixture turned translucent, the sample was then poured onto a dish and dried for between 3 to 21 days. 5 trials were conducted, 2 on glycerol only, 2 on glycerol and PVA, and 1 on glycerol and sugar. The variables kept controlled were the proportions of ingredients added to the beaker, the heat time, the heat level, and drying conditions. The flexibility and tensile strength of each bioplastic was tested qualitatively by bending and pulling each sample by hand, with my results recorded on a 1 to 5 scale as outlined here. The results show that the glycerol-only samples were the most flexible but the weakest. Adding PVA glue kept the flexibility and boosted tensile strength, while the sugar mix stayed flexible but only had moderate strength. The bar graph here shows how different additives affect the balance between flexibility and tensile strength. The data collected mostly aligned with the hypothesis. Glycerol-only films were highly flexible but weak, supporting the idea that glycerol disrupts hydrogen bonding between starch chains, increasing flexibility but reducing tensile strength. Glycerol glue samples maintained a similar flexibility but with improved strength, likely due to the PVA forming extra hydrogen bonds that stabilize the polymer matrix, matching the predicted range of tensile strength. Unexpectedly, the sugar sample was more flexible than hypothesized. While sucrose is meant to encourage crystallization and brittleness, the flexibility observed may have resulted from a mismeasurement of excess glycerol or moisture interfering with the intended additive ratio. Validity was attempted to be maintained by keeping controlled variables like heating temperature, drying time, and starch amount, etc. constant, and only changing the additive composition. However, due to time issues, the first glycerol sample ended up drying for almost 5 times longer than the others, so the validity was not necessarily upheld to the whole experiment. Improvements could include having a more consistent sample thickness and more precise measuring tools, such as more precise scales. The reliability was also low due to the limited number of trials, especially for sugar, which fell short of the recommended 3 per variable. Improvements here would simply involve adding more trials. Error largely came from the qualitative testing and one experiment which had a faulty scale, which caused a mistrial due to the ingredients being measured wrong. Improving things like this would involve using a more quantitative data collector, such as a force meter for the tensile strength. Limitations included the small quantity of bioplastic produced in the experiment, as it was prone to lumping and heating it for the outlined time often resulted in a product that was hard to spread into a film, as well as the basic equipment available due to the constraints of conducting the experiment in a high school. In conclusion, this experiment confirmed that additive composition significantly affects bioplastic properties, overall supporting the hypothesis. Glycerol increased flexibility, scoring a 5, but lowered tensile strength to a 1.5 as predicted. Adding PVA glue maintained a high flexibility at 4, while improving tensile strength to 3, aligning with the hypothesized range once more. The sugar sample was less consistent. Despite sucrose's tendency to promote brittleness, the flexibility remained unexpectedly high at 4, though its tensile strength was still low as expected at 2. These results demonstrate how molecular interactions shape polymer properties and emphasize the value of these findings for designing purpose-specific bioplastics.